Lines were there for the
some sir speaker
speaker will be introduced by the chair.
Yes, sir. Professor Harold Upmir and chair is Amin Shofi.
Yes, sir.
Yes, sir. You can introduce Amin Shofi. So Amin Shofi, sir, will introduce as speaker, sir.
Okay, sir.
I'll just welcome and I'll hand over the session to you, sir. I think Das has shared you the certificate.
Yes, sir.
So after some time, I'll make you as a host and I'll leave, sir, because 3 o'clock another one is there. So that at the end you will take care, sir.
Okay, sir. Fine.
Yes, sir.
Fine, sir.
Fine.
I think the speaker's information is there with the chairperson, right, sir?
Yes, available, sir. I think you know, sir. Speaker and for the chair information.
Chair information is there. Only
yes, the speaker, sir, will take care, sir.
Okay, sir. The YouTube and live will take care, sir.
Sir, YouTube already started. It's just started.
Okay.
I'll just send you the YouTube link.
Yeah, it's going on here. Yes.
I'll put you in your WhatsApp, sir.
Fine, sir.
Sir, I have given certificate. You downloaded, na, sir?
Yeah, it is there on my desktop.
Okay, okay. And you rotated, na?
Yes.
Yeah, yes.
Okay, 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 sir.
Just I have to show it, right?
You have to request to announce.
Yeah, I know.
After that, you display.
No, it's the only display.
Yeah, yeah, yeah.
Yeah. The speaker has come, sir.
So, can you hear me?
Yes, very good afternoon.
Thank you.
This is Dr. Nageshwar Rao.
Mhm.
I'm the hosting this session. So I think we have some 5 minutes of time. I think others will join. Waiting for the others to join, sir.
Very good.
Sir, welcome, sir.
Thank you.
Yes, sir. I'm just checking whether you are audible and whether chair the session joined.
Yes. So you can hear me?
Yes, yes, sir. Yes, sir.
Very good.
Thank you very much for joining.
Thank you.
Sir, thank you very much for joining. I'm just checking whether our chair the session joined. Sir, what is the time right now at Germany, sir?
9:26
Oh,
a.m.
fine. We have now around 1:56
Yeah, still 4 minutes.
p.m. So it may be. Sir joined. Sir, Sophie, sir, welcome, sir.
Thank you.
Good afternoon, Rishiji. Yeah.
Sir, good afternoon. Yes. So now both of you joined. We have 4 more minutes to go.
Actually, there was a power breakdown just minutes before.
Oh, fine, sir. Fine, sir. Now it's still 3
Okay.
more minutes is there, sir. So this is another important plenary talk. After this, we have 2 important symposiums. One is on history of mathematics. Another one is on industrial mathematics. Again, in industrial mathematics symposium, there are 2 professors from Germany is delivering their talks, and one from Poland delivering the talk in the symposium on industrial mathematics. So this is another important symposium. So I'll also introduce Professor Nageswar Rao. He is the co-chair and he is also involved in this session.
Good afternoon, sir.
Professor Rajadas is also there, sir, from our VIT. Let's wait for 2 more minutes. Sir, already I made you as a co-host so that you can able to share your screen.
Right. That's what I was going to say. Yeah.
Good afternoon, Godadarji.
Hey, yeah. Hi. How are you? You are from Srinagar or?
I'm in Srinagar. Yeah, wearing at least 5 layers of clothes right now.
Yes.
It was -7 during the night.
Oh God. Yeah. But as we all know, perhaps this is not the time, but you know, that's not the only difficulty out there, right?
Yeah.
Yeah, you have to cope with several aspects of life, and I hope you are you know, doing well. As you said, we are not able to travel, see each other, but
Yes.
let's hope.
Yeah, actually, I had plans to go a few places this winter, but then that was not to be.
Yeah. No, it's best not to travel anywhere at all right now. Yeah.
So you are in Bangalore right now?
No, I am with my daughter in Gandhinagar, Gujarat.
Gandhinagar, okay.
And I don't know when I'll be going back to Bangalore, even if it is for a few days. So we'll see.
Sir, Sir Satyadev, sir, your voice is muted. Satyadev, sir, please unmute, sir.
Yes, now can you hear me?
Yes, sir.
Gadadhar Mishra.
Yeah,
How are you?
hello. How are you? Good
I'm fine.
afternoon. Yeah.
Yes, good afternoon.
Good night. So you are in Allahabad, or where are you?
No, I'm in Allahabad.
You are in Allahabad. Okay, I mean,
But
no, I
not
was
in
just
HRM.
wondering. I mean, is that where you know, you have decided to stay, or?
Yeah, actually, HRI was closed. Now it is opening, of course. But I have been here since lockdown was started.
Right.
So I'm in my home.
Okay,
Yeah,
okay.
I'm in my home in
I see.
Allahabad.
Yes. Good. Yeah. We are all sort of, you know,
In the same boat.
Input. Yeah. Right.
Sir, may I start now?
Yes. Yeah.
So welcome all of you. On behalf of IMS 2020 and VIT Organizing Committee and also Indian Mathematical Society, it is a pleasure and honor for welcoming all of you for this today's important plenary session by Professor Harold Upmir from University of Marburg, Germany. We may talk about operators and Hilbert modules on bounded symmetric domains, chaired by Amin Shofi. So I now request my colleague, Professor Rao, to introduce the chairperson.
Thank you, sir.
Over to Nageswar Rao.
I, Dr. R. Nageswar Rao, on behalf of IMS Organizing Committee, VIT Vellore, welcome the dignitaries, participants to this session of 86th Annual Conference of Indian Mathematical Society. I warmly welcome the speaker for this plenary talk, Professor Harold Upmir from University of Marburg, Germany. I also take this opportunity to welcome the chairperson of this event, Professor Amin Sofi. Professor Amin Sofi is presently adjunct professor at Central University of Kashmir, Srinagar, India. He was formerly professor at Kashmir University, Srinagar. Now I humbly request Professor Amin Sofi to introduce the speaker and take over the session. Over to the chairperson. Thank you, sir.
Good afternoon, everybody. I welcome you all to this plenary talk by Professor Harold Meyer from the University of Marburg, Germany. It's very difficult to sum up his outstanding achievements in a couple of minutes, but I would like to settle for a very brief description of his major achievements in mathematics. So right now, as I said, he is professor of mathematics at Marburg University in Germany. And he is also holding an Infosys visiting professorship at the University of Science, Bangalore. He's a fellow of the American Mathematical Society. He did his PhD from the University of Tübingen in 1975 and his habilitation from the same university in 1982. And he has been has held various professional positions from 73, beginning at University of Tübingen, then University of Pennsylvania, University of Kansas, then again as full professor at the University of Kansas, and now he's a professor at the University of Marburg. Some of his selected, some visiting positions include at the University of Edinburgh, Scotland, and then Instituto Superior Técnico at Lisbon, Portugal, Mathematical Science Research Institute, Berkeley, Mittag-Leffler Institute, Stockholm, Erwin Schrödinger Institute of Mathematical Physics in Vienna. He is also on the editorial board of Math Nachrichten and of the Journal of Integral Equations and Operator Theory. His major conference addresses include as a principal speaker at the CBMS Regional Conference on Jordan Algebras in Analysis, Operator Theory, and Quantum Mechanics at Irvine in 1985, and invited our address at AMS meeting in Fargo 1991, and then at AMS Research Institute on Quantization in the US at Holyoke in 1996. He also had given an address at IVOTA Congress in Fargo, Portugal in 2000, and then on a workshop on quantization at UC Berkeley 2001. He has been a regular visitor to India and has been lecturing extensively, especially at ISI Bangalore, ISI Bangalore, and IMA Bhubaneswar, Odisha. His main books include Symmetric Banach Manifolds and Jordan Sister Algebras from North Holland, 1985. Then from the AMS publication in 1987, his book on Jordan algebras in analysis, operator theory, and quantum mechanics. Then his multivariable Toplitz's operators and index theory in Berkhauser. Zero differential operators on symmetric cones in the CRC Press 1996. And also acted as editor and contributor to the proceedings on non-commutative geometry and the standard model of elementary particle physics. I'll just briefly mention 4 or 5 of his outstanding publications out of a whole lot of many that he has written over the years. Jordan Algebras and Harmonic Analysis on Symmetric Spaces in American Journal of Mathematics. Toplitz's operators on bounded symmetric domains into transactions. Toplitz operators and solvable C-star algebras on Hermitian symmetric space in the Bulletin of AMS. Toplitz C-star algebras on bounded symmetric domains in the Annals of Mathematics. And one in Mathematician Annalen, one of them, on Toplitz operators on symmetric Siegel domains. And with our own Professor Gadadhar Mishra, his joint work on homogeneous vector bundles and intertwining operators for symmetric domains, which had appeared in Advanced in Mathematics. There are lots and lots of many more, but I would like to settle for this brief description of his very epoch-making achievements. I'll now leave the floor open, to Professor Meyer to give his plenary talk.
Thank you,
This will
Professor
be
Sophie.
from 2 to 3. Professor Meyer.
Yes.
Yeah, I leave the floor open to you.
Thank you. Maybe you have to allow the screen sharing.
Yes, the screen sharing is fine. You can make it full screen by going to your right, and then there is that little arrow. If you push on that little arrow, yeah, that's
yeah, it's okay.
Now
Yes,
it's fine.
fine. Yes.
Yeah, that's okay.
So thank you once again for the kind introduction. And let us start. So the topic is Triplets, operators, and Hilbert modules over bounded symmetric domains. I hope you can all hear me fine.
Yes.
Yes, yes.
This is okay. So a joint appointment at Marburg and the IISc in Bangalore. Let us first start with some background on bounded symmetric domains. Of course, classically, they are defined in terms of Lie theory, Lie groups, namely a bounded symmetric domain is a quotient manifold G mod K. So let us call the domain D is G mod K, where G is a semi-simple Lie group. Of course, we want the non-compact type because we have domains. We want the Hermitian type because we want complex domains in complex spaces. And the K is a subgroup of G, actually a maximal compact subgroup. And the complex structure of the domain needs that the K has a non-discrete center, usually one-dimensional. And that center generates the multiplication by I. The complex structure is generated by the center of K. So that is the usual definition of symmetric spaces in Lie theoretic terms. Harishchandra found out that such a domain has a realization called after him as a convex circular domain. That means actually as a unit ball in some norm in a complex vector space which I always will call capital Z. So capital Z is my notion for a complex vector space where the domain D lies in, and in such a way that the group K is the stabilizer group at the origin, and then consists of linear transformations. Of course, the group G consists of nonlinear transformations because it has to be transitive on the domain, but K consists of linear transformations. Let us start with the most basic example. Namely, let's take the matrix space. Capital Z is the R by S matrices, R less or equal to S, say, and then we take the operator norm, the usual operator norm on the space of matrices. Then, of course, we obtain the matrix unit ball, D, all matrices of norm less than 1 in the operator norm. You can also write it in the sense Z, all matrices such that identity minus ZZ star is bigger than 0. You could also put the star on the left. That would be the same condition. So this roughly means that all singular values of the matrix have to be less than 1. That is the condition. That is a symmetric domain. And what is the group G? Well, it's a very concrete one. It's the unitary group, more precisely the pseudo-unitary group, because we want non-compact domains of signature R, S. R and S were these ranks of the matrix. So these are all block matrices A, B, C, D in GLR plus S, big matrix, which are unitary with respect to this matrix 1, 0, 0, minus 1. They have a kind of 1, 0, 0, minus 1. Usual pseudo-unitary group. And it acts on the domain D via Möbius transformations, linear fractional transformations, just as in the classical case, but we must be careful since we have matrices. Of course, we cannot use quotients. We have to take AZ plus B, CZ plus D inverse in the matrix sense. You could also put the -1 on the left. That is also possible. So it's a direct generalization of the unit disk, where you have the fractional linear transformations. And the group K, remember, it has to stabilize the origin, keep the origin fixed. That means that the B and the C are 0. So it's just the diagonal matrix, A0, 0D. And it acts, if you look at the Möbius transformation, by linear transformations, Z maps A, Z, D star. So that is the basic example. Now, I come to my main point. As Professor Sophie has already pointed out, my area is the so-called Jordan algebras, and a refinement of the Lie theoretic description of symmetric domains is the Jordan theoretic description. Let us quickly go over this. We start with Harishandra's realization in a complex vector space capital Z, but now we put an additional structure on that vector space, so-called Jordan triple product. So as the name says, it is a ternary composition. 3 vectors x, y, z go into a new vector, which is denoted by these brackets. That is, it is a generalized anticommutator, and the physicists denote anticommutators by braces, x, y, z. Now, the condition is it must be bilinear in the outer variables, x and z, even symmetric. It must be conjugate linear in the middle variable. And there is a certain Jordan triple identity that looks a little bit like the Jacobi identity in Lie algebras, which I will not write down. Now, once you have such a triple product, one can recover the domain D as the so-called unit ball in the spectral sense. Remember, in previous case, we had the singular values had to be less than 1, and this can be done in general, and you get the so-called spectral unit ball. So let us look at this in the example of the matrix space. C is CR by S, and the triple product is the generalized anticommutator, x, y star z plus z, y star x. recall that this makes sense even for rectangular matrices. If you have square matrices, you could put y equal to the identity, and you would get the usual anticommutator, xz plus zx. But this is more general, that is the triple product. For example, many people are interested in the usual unit ball in CD that corresponds to the rank 1 matrix. So it would be rows instead of matrices. And then this Jordan triple product has the form xyz becomes the inner product of xy times z plus inner product of zy times x, because it need to be symmetric in the outer variables. And of course, in the one-dimensional case for the unit disk, there's not much structure. XYZ Jordan triple product is 2 times xy bar z. The 2 is simply because I do not divide by half. 2xy bar z. So this is a quick introduction into the Jordan description, which plays a major role later. Let us get an overview over all possible Jordan triples, which by the previous sense is also an overview over all irreducible symmetric domains. Namely, these things are classified. Irreducible Hermitian Jordan triples are classified. They have a rank R, which for matrices is, of course, the matrix rank, CR by S. And they have two more so-called characteristic multiplicities, A and B, which I will now explain in the list. We first have the full matrix triple, which I described with the anticommutator. Here the rank is, of course, R, if R is less or equal to S. The number A is 2, so we speak it's the complex case, 2-dimensional. And the B tells me whether it is of square type or not. So B is S minus R. Second case is the so-called symmetric matrices under the usual anticommutator product. Here A is 1, so it is kind of the real case. Antisymmetric matrices would A is equal to 4, so that would be kind of the quaternion case. So you see all the division algebras show up, real numbers, complex numbers, quaternions. But there is a little more. There is another class, the so-called spin factors, which have rank 2, but here the A is arbitrary. The B is 0, the A is arbitrary, greater or equal to 1, and they are related to the representations of the orthogonal group, spin group and orthogonal group, and Lorentz geometry. So a lot of geometry lies in the spin factors, although they have very small rank. R is just 2. And then the worst are the two exceptional Jordan triples. One is of dimension 16, and one is of dimension 27. And you see already these are numbers related to the number 8 somehow. And it is actually defined over the Cayley numbers or the octonions. This is also a division algebra, but not associative. So it's more difficult. That's why they are called exceptional Jordan triples. So you have essentially 6 classes: full matrices, symmetric matrices, antisymmetric matrices. They kind of belong together, of course. Then you have the spin factors of rank 2. And then you have 2 more triples, only 1 in each class, of dimension 16 and 27. The 27-dimensional was discovered by Jordan, von Neumann, and Wigner in the old days of quantum mechanics. They discovered the 27-dimensional Jordan algebra. Okay, if B is equal to 0, remember that was in the first example, for example, the square matrix case, one says that D is of tube type. This is related to number theoretic questions, realizing D as a tube domain over a convex cone. And in this case, Z has a kind of a unit element, and you can put in the triple product, you can put the unit element in the middle, of course, ZEW, and you get the usual anticommutator. And that becomes a Jordan algebra. So Jordan algebra is roughly the case, the special case where the B is equal to 0. Now for later, we need 2 numbers. D is the full dimension of my domain, R is the rank, and it is easily shown, well, with some structure, that D over R can be expressed by these numbers A and B, these multiplicities. And if you delete the B, you get, so to speak, the tube type dimension, D sub E over R. E stands for this unit element E, where the B is missing. So this will play a certain role later. Let us quickly go over some applications, some major applications of symmetric domains. Here I'll be rather quick because it's not my main topic. One area of applications is, of course, representation theory of the semi-simple Lie group G by holomorphic transformations of D. Well, Harishchandra, of course, invented the discrete series and kind of classified them in an indirect way. But for the holomorphic discrete series, he found an explicit model. And that is the holomorphic discrete series is given by Hilbert spaces of holomorphic functions on the domain D, possibly vector valued. Today, I will mainly look at scalar valued, but the general case would be vector valued. So these are the so-called weighted Bergman spaces. Why is this so? Because every bounded domain has a classical Bergman space that is at the heart of a differential geometry on the bounded domain, the Kähler geometry. And so we call these generalized spaces weighted Bergman spaces. Now, if we want the non-holomorphic discrete series, they exist. They can still be realized on the domain D by, instead of holomorphic functions, you take cohomology classes of the D-bar operator, the so-called L2 cohomology. And this was one of the achievements of Indian mathematics, also mentioned in the previous talk by Narasimhan Okamoto. If you want to go further and look at the arbitrary series, non-discrete series, that is more difficult. These are needed for the full Plancherel measure, and there one needs not the domain D, but so-called satellite domains that are not pseudo-convex anymore, but they are still G orbits in a Grassmann type manifold. And that is very interesting mathematics. The so-called Penrose integral transform shows up, and double fibrations play a major role here. So that is kind of an outlook. A second type of applications concerns discrete subgroups of the group G. So if you have a discrete subgroup gamma in G, of course, you can look at automorphic forms and modular functions on the so-called Shimura variety, D mod gamma, which is a double quotient. It's a well-known construction, of course, in number theory. For example, the Jordan triple of symmetric matrices gives rise to Siegel modular forms corresponding to the discrete subgroup symplectic group with integer entries SP2R of Z as a subgroup of the symplectic group of the full symplectic group. This corresponds to the symmetric matrices. One can also do this for the full matrices and for the antisymmetric matrices. Even for the spin factors, these are the famous Cougar varieties that you get, but for the exceptional domains, it is more difficult. But the Jordan algebraic approach leads to new number theoretic concepts beyond the complex and quaternion case. Now, a final remark, in the operator theoretic context, introduced later, discrete subgroups would lead to von Neumann algebras which are not of type 1. I lectured on that in Bangalore last winter, but so far the theory is rudimentary. Okay, so now let us come to our main topic, operator theory. And this will now be a little bit more technical, of course. So we start with one of the highlights of representation theory, one of the most beautiful theorems in representation theory, namely the decomposition of the algebra of polynomials. So let P of Z denote the algebra of all polynomials on my Jordan triple Z. So Jordan theory allows you to take a completely uniform point of view, independent of the classification, and that is very nicely presented here. Of course, the group K acts on polynomials by the usual pullback action. K dot f of z is f of k inverse z, clear? But of course, it is not irreducible. For example, the total degree of a polynomial or total homogeneity would of course be preserved because K is a linear action. But even the homogeneous polynomials of a fixed degree are not irreducible. But Wilfried Schmid and Constant and many others found out that for symmetric domains, it is completely uniform. Namely, we have a Peter-Weyl decomposition, P of z, summation Pm of z. What is the M? Now the M ranges over all partitions. So that is the main idea. What is a partition M? Well, it is an array M1 greater or equal to M2 up to Mr greater or equal to 0 of integers of length R. R is the rank. The rank is, of course, the crucial ingredient of a domain. And the PMZs are irreducible K modules. So these are the irreducible K types, as one says. And of course, it's uniquely determined by the highest weight vector. So all I have to do is to write down one vector. And that was actually my paper in the American Journal of Mathematics, where I found this vector in a completely general form. Namely, it is a product of determinants n1 to the power m1 minus m2, n2 to the power m2 minus m3 up to nr, mr, where these ni's are certain Jordan determinants. We have seen the classification, of course, for matrices. The Jordan determinant is more or less the classical determinant. For the spin factors, the determinant would be the Lorentz metric. And for the exceptional domains, it's even more complicated. But the Jordan determinants exist all the time. And this was my formula that I found. Of course, obviously nice. And the partition goes in very nicely as the powers of the successive minors. And one has degree 1, and 2 has degree 2, and R has degree R of these determinants. Let us look at one simple case. The simplest one is, of course, 1, 0, 0, that is a partition. There one obtains just the linear forms. So the linear forms are, of course, irreducible under K. But of course, already the quadratic polynomials are not irreducible, but you need the decomposition into partitions. If the rank is 1, of course, there is no partition. A rank M would just be a positive integer. There, Pm of z is really the M homogeneous polynomial. So for the classical unit ball, there is no combinatorics. There is just the homogeneous polynomials. But in higher rank, you need these partitions. So this is obviously a very beautiful and general theorem. And it will be at the heart of what we will do next. Now, the completion of the polynomials under the so-called Fock inner product, Fisher-Fock inner product, which is the inner product over the domain, over the space Z with the Gauss measure, e to the minus ZZ is a Gauss measure. Okay, the usual Fock inner product. And the completion, which I denote by H2 of Z, somehow the first line is a little less visible than the others, is called the Fock space, obviously, or also the Siegel-Bachmann space. There is a famous historical history behind this second name, Siegel-Bachmann. They were not collaborators, but competitors, but still, it's the Fock space or Siegel-Bachmann space. And of course, it plays a fundamental role in many, many parts of mathematics. Its reproducing kernel is simply the exponential k of zw e to the power zw. Now, since we have this Peter-Weyl decomposition, the reproducing kernel can be written in a kind of a Taylor expansion, which I denote by em of zw, ranging over all partitions. And how are these EMs defined? These are polynomials, holomorphic in Z and anti-holomorphic in W, which are given roughly as a usual kernel. Namely, you take an orthonormal basis of your space Pm of Z. These were these irreducible K modules. And you take C alpha M of Z C alpha m of W bar. That's the usual way to write down a kernel function. Note that it is homogeneous. It's a homogeneous kernel. And so this would be the reproducing kernel of PMZ itself as a finite dimensional subspace of H2 of Z. Let's fill this a little bit more with life. The simplest partition 1, 0, 0 of the rank 1, you get the inner product. So E1, 0 is normalized inner product on Z. Again, if the rank should be 1, that is not my main point, but if the rank is 1, of course, the EMs are just the powers, because everybody can expand e to the ZW into homogeneous parts, which would be ZW to the M or M factorial. But this is not true anymore. Even in rank 2, you get the so-called harmonic polynomials, which are kind of hard to describe. So in general, these are these Fisher-Fock spaces E sub M, the parts of the Bergman, of the Fock kernel. Okay, but we are really not interested in the Fock space, but in the Bergman spaces. Remember, this is the holomorphic discrete series of the group G. We need one invariant, which is called the genus 2 plus A R minus 1 plus B, so-called genus. It's actually, yeah, that's gives the invariant measure. Let's leave it like that. And if you take a parameter nu bigger than p minus 1, one less than the genus, one can define a measure, a probability measure, according to the formula that is following. And we define the weighted Bergman space H2 nu of D. So H stands for holomorphic, 2 of course for square integrable, and nu determines this invariant that I want to discuss. It consists of all holomorphic functions on the domain, and the inner product. Remember, for the Fock space, we had the exponential, the Gauss measure. But now it's more complicated. What we have is, it is a power delta of z to the power nu minus p. P is again this genus. The rest is more or less the same. C nu is a normalizing constant. But what is the delta? Well, the delta is a sesquipolynomial, the Jordan triple determinant. So that is obviously a crucial thing. I've talked already a lot about determinants, but this one is new. So delta of z comma w is not homogeneous. So let us write it in for matrices. It is the determinant of 1 minus zw star. So this kind of is a new construction, of course. And as I mentioned already, it comes from the invariant measure. The group G, of course, has a Haar measure. And if you want to write down the Haar measure, you get this delta. So delta will be the Jordan triple determinant, the inhomogeneous one. And one of the triumphs of this approach is that the reproducing kernel of H2 nu of Z can now be written very explicitly as the negative power of the determinant. So K nu of Z comma W is delta of ZW to the power minus nu, the negative. That is the same as for the Fock space. Where we had the Gauss measure e to the minus zz as the measure, and the kernel was e to the plus zw. So it's a kind of the inverse of the measure, the reproducing Bergman kernel. That is a very beautiful and general formula. Even in the rank 1 case for the unit ball, it becomes nice. In this case, delta of zw is 1 minus inner product of zw, and k nu is the negative minus nu. And nu is bigger than d, that is the scale of Bergman spaces for the unit ball, because p is d plus 1 in that case. Okay, now I refer back to the Peter-Weyl decomposition. Since we have the holomorphic functions decompose into these irreducible k-types that we discussed, this also explains that the reproducing kernel, which is delta ZW to the power minus nu, can be written as a power series in these Fisher-Fock kernels, EM. Okay, That is true for general principles. When we had the Fock kernel, the e to the zw, we just had unity for the coefficients, just summation of the em. That was the condition. But of course, in the weighted Bergman spaces, you need a coefficient. And Farot and Korani found this formula, found the coefficients, namely the so-called Pochhammer symbol. Pochhammer symbols are well known in combinatorics, of course. So nu sub m, well, it is a product from 1 to r over ordinary Pochhammer symbols, quotient of gamma functions. This you know, have heard about, but it is a shifted one. So if I take the mj is the jth part of the partition, then I have to subtract nu minus a half j minus 1. So it is kind of a shifted one that actually comes from representation theory of the Iwasawa subgroup of G. G has an Iwasawa decomposition, as you probably know, and if you look at the measure there, you get these shifts, nu minus a half j minus 1, and if you take the Pochhammers and take the product of those, you get the so-called multivariable Pochhammer symbol. So the important point is it's a product. It is of product type of ordinary Pochhammers. Simon Gindikind was one of the major contributors to all this theory, but the formula is due to Farot and Korani. So the equivalent statement is that the Bergman and the Fock inner products are related by the formula that the Fock inner product of two polynomials is nu sub m, the Pochhammer, times the Bergman inner product. The two are proportional on each irreducible k-type, and the proportionality factor is this. Now, as a general concept, the so-called Wallach set is the set of all parameters such that the kernel function that I wrote down, delta zw to the minus nu, is positive. This means positivity in the sense of kernel functions. So if you take a finite number of elements in your domain, the according matrix must be positive. That is the condition. And then you get a reproducing kernel Hilbert space by abstract construction, not necessarily coming from a measure on D or on its closure. The weighted Bergman kernels came from a measure, but generalization would be an arbitrary one. And the Farot-Korani formula shows that positivity of this kernel, remember that Farot-Korani said all these numbers nu sub m must be positive. All these Pochhammers must be positive, and one can easily show that this means it has a continuous part, nu bigger than a half r minus 1. For rank 1, it would be nu bigger than 0. But in general, it is nu equal a half r minus 1. And a discrete part, L a half from 0 up to r minus 1. So this is the analytic continuation of the holomorphic discrete series. We look only at the continuous part. Well, there the kernel is still positive definite instead of just positive. And the polynomials are contained in that new Hilbert space as a dense subset. So nothing really changes beyond the weighted Bergman spaces. In particular, we have one important parameter, dimension over R, given by that formula, which is the Hardy space over the Shiloh boundary of the domain. You know, of course, the Shiloh boundary of the unit disk is the circle, and the Hardy space over the circle played a major role, of course, in number theory. And this can be generalized in general and corresponds to the parameter D over R, which is not a weighted Bergman space. It's beyond the discrete series, but it is still in its analytic continuation. Let us come to Turbulent operators. If you have a bounded symmetric domain and the weighted Bergman spaces, actually I can also do the more general ones, but let us stick first with the weighted Bergman spaces. We have an orthogonal projection because we have a measure. We had this measure that was the power of the determinant. And then we define the Triplets operator, Tf of phi, to be we first multiply f times phi, where f is a function on D and phi is holomorphic, but the result will not be holomorphic anymore, and we have to project down with the projection P. So that is the usual definition of a Triplets operator, and it is a bounded operator if the function f is bounded. But f need not be holomorphic, just measurable or smooth. Well, some of my papers were mentioned in the introduction. If you look at the C-star algebra, script T, generalized by all Triplets operators with continuous symbols up to the boundary, then you have a very interesting stratification of the Triplets operators of length R. The smallest ideal I1 is the compact operators. Then you have another one, I2, I3, and so on. IR is the commutator ideal, which for rank 1, of course, agrees with the compact operators, but not in general in T. And the point is that each successive subquotient, so if you take two successive ideals, ik plus 1 ik, are essentially commutative. So in that sense, I won't go into details here, but in that sense, T is a non-commutative model of the underlying domain, together with its boundary stratification. And in fact, there is a lot of activity recently on finding the K-theory of the C-star algebra and so on. All this holds also for parameters in the continuous Wallach set, in particular for the Hardy space. The theory is roughly unchanged. Okay, now the weighted Bergman spaces carry an irreducible unitary representation. Actually, that's how we started. We wanted to describe the scalar holomorphic discrete series. In this case, it's very concrete. G acts on a holomorphic function by pullback phi of G inverse of Z multiplied by a cocycle, namely the Jacobian to the power nu over P. P is again this genus. So for example, if nu is equal to P, that is the standard Bergman space, it would be the ordinary Jacobian. So this is the so-called scalar holomorphic discrete series. Now one can show that the Triplets operators are covariant under this group representation. Gadara-Misra calls this a system of imprimitivity. So T of F circle G inverse is U nu of G, TF U nu G inverse. So they are kind of compatible for any symbol function F. Therefore, of course, there are no operators that are G invariant except for scalars. But if you restrict to the subgroup K that acts reducibly without multiplicity on the domain, so there exist interesting invariants of operators that are invariant under K of Triplets type. Now, because the group K acts multiplicity free, any K invariant operator is uniquely determined by the sequence of eigenvalues. It's a little bit like the Pochhammer symbols. So TPM is equal to PM times tau of m. Tau of m is my eigenvalue, and that would hold for all PMs in the irreducible K type. So a K-invariant operator is uniquely described by giving the eigenvalues for any partition n. That is the task. Now, I cannot do it in general, but I found a very nice, two nice formulas for the eigenvalues of certain partitions. So let me describe this quickly. Remember the Jordan triple determinant that was determinant of 1 minus ZW star, an inhomogeneous one. But of course, it has a decomposition into homogeneous parts, summation from 0 to R minus 1 to the L delta L of ZW into sesquipolynomials delta sub L, which are homogeneous of by degree L comma L. These would roughly correspond to the elementary symmetric functions. If you expand usual determinant into such a form, you would get the elementary symmetric polynomials. Well, these delta L can again be described up to a constant via an orthonormal basis of PL of Z, where now L is my basic partition 1, 1, 1, 0, 0, but I do not only have a single one, but I take all of them. These are the so-called fundamental representations of the group K. Every Lie group has a set of fundamental representations, which obviously are the most important ones. And here it is these ones, the partitions L, but which have L ones and the rest is 0. So it could be 1, 0, 0, 0, or all of them 1. That would also be possible. So I can do all of them simultaneously. If I have no ones, I get the constants. C, that is not interesting. But for L equal to 1, delta 1 is the inner product. So summation Z ui UIW. So let us look at the triplets operators that belong to these partitions. What we will do is we determine the eigenvalues of K-invariant triplets operators, actually 2 of them. And it turns out one is slightly easier than the other one. The first one is the ordinary triplets operator, whose symbol is this delta L polynomial. It would be of the form T phi alpha star, T phi alpha. So please note the star is on the left. But if you look at the sesquiholomorphic functional calculus, you could also do the converse. You could plug the triplets tuple into the polynomial delta L, and that would mean that the star is on the right. And they are not equal because of non-commutativity. Both of them are K-invariant, and they correspond to the contravariant and covariant symbol in the sense of Bayesian quantization. The first type is a little more difficult than the second one. So in particular, if you have L equal to 1, of course, you would get just linear functionals, the star on the left or on the right. And that was discussed at the Indian Institute of Science in last winter. So in order to express my result, take any partition and make a little shift. Mk prime is Mk, and I subtract a half k minus 1. We have seen such a shift already in the Pochhammer symbols. And now I define 2 constants. This will be, of course, given in the write-up, so let me be a little quick here. Alpha M upper L and beta M upper L for any subset of 1, R of arbitrary elements L. And so it is a double product, K in L, H not in L. The beta is similar. But the main point is it involves differences of the partition entries, Mk minus Mh. Differences is more difficult than the Pochhammers, which only involve a single element. So these are the 2 elements, alpha Lm and beta Ml. And if alpha M plus chi L is not a partition, then we put 0, and also for the beta. So there are 2 combinatorial numbers. And so they involve differences, as I mentioned already. And here are my 2 eigenvalue formulas. Namely, let us first look at the easy one. You plug in the triplets tuple into the polynomial, so functional calculus. The formulas look all the same. So I explained one of them, and the rest is similar. So delta L of t has the following eigenvalues. L is, of course, between 0 and R, and you take summation over all subsets of that size. The first quotient is just ordinary Pochhammers, so that is not surprising. But the main point is the beta shows up, beta ML, for the Fock space. And if I take the weighted Bergman space, it is clear I have the nu has to show up somehow, but the basic structure is unchanged. The Pochhammers involving the nu show up, but that is all. So very uniform. Second eigenvalue is the harder one, and that was open even for L equal to 1. So that is really the new one. If you now take conversely the triplets operator of that delta L, you get the same thing, but the alphas show up. All first in the Fock space and then in the weighted Bergman spaces. So these are 2 eigenvalue formulas. Let us do quickly what happens in the special case L equal to 1. Well, the first eigenvalue is given by this, rather explicit, and that was already obtained by Araji and Zhang. And I could do the higher rank L equal bigger than 1 using results from combinatorics, in particular a Peary formula due to Kevin Cadell and Richard Stanley. So that is the main input. Because of lack of time, let me... the second formula, the harder one, would look like this in my case, and it was conjectured by Gara, Kumar, and Pramanik and proved for them for all domains of rank 2. That was actually the starting point of my investigation. So here I list the cases where rank 2 domains show up. Now, for higher rank, unfortunately, the method of Gara, Kumar, Pramanik does not work because they have only 2 equations. That is not enough if the rank is bigger than 2. So instead, I use a skillful sure orthogonality and a reciprocity result on the dimensions of the PMs. I kind of computed the dimensions long time ago, and this is obviously a nice reciprocity for the dimensions, and that is used in the second case. So in the remaining minutes, let us quickly point out goes to Hilbert modules. So the theory of Hilbert modules, pioneered by Ron Douglas, is a refinement of operator theory, namely where methods from complex analysis, Hermitian differential geometry, and homological algebra show up. For example, for any bounded domain in CD in a Hilbert space of holomorphic functions, I will only use scalar valued functions, is called a Hilbert module if for any polynomial P, the multiplication operator by this polynomial is bounded on H. Then one can, of course, look at the adjoint operator, MP star, and these have eigenvalues. That is the main point. And we can take the joint eigenspace V sub W. So these are all elements in my Hilbert module H, such that MP star of phi is a multiple of phi, and the eigenvalue is P of W bar at any point W in D. So we take the disjoint union of all these eigenspaces. It becomes a subbundle of the trivial vector bundle, of course. It lies in D cross H. And I call this the eigenbundle of H, although it is not locally trivial in general. So every Hilbert module has this eigenbundle made up of the joint eigenspaces. Now, assume as usual that we have a reproducing kernel function given by an orthonormal basis. So H is the closed linear span of the holomorphic functions K sub W of Z, where I fix the second variable. Okay, that is the usual approach of reproducing kernel functions. Now these kernel functions KW belong to the module VW. That is easy to show. Cohn-Douglas theory concerns the case where this is all. So where V sub W is spanned by the K sub W, which would result in a locally trivial line bundle in our case. But in general, the eigenbundle will have higher dimension. It will jump up, the rank will jump up at certain singularities, and the appropriate framework for these singular Hilbert modules are the so-called linear analytic spaces from the theory of several complex variables, which are known to be in duality with the category of coherent module sheaves. So here we now go deeply into complex analysis. The Cohn-Douglas setting is essentially the locally free sheaves, which is obviously a very special case. Let me just mention in passing that the typical example would be the Hardy space over the bidisk. So all holomorphic functions on the bidisk, the I less than 1 evaluated on the Shilov boundary, and take the submodule of all Hardy functions vanishing at the origin. If you take this, the kernel can be written down. I've done it here, one shows that the eigenbundle is always one-dimensional, except at the origin. And at the origin, it blows up and becomes two-dimensional, spanned by Z1, Z2. Now, Biswas, Misra, and Putina have developed a general theory covering such phenomena. It mainly works for complete intersections, where your variety is smooth, given by a regular sequence of polynomials. Now comes my own contribution, namely I will now define modules and eigenbundles which do not come from complete intersections. What are the singularities of a symmetric domain? Well, you take all elements where the rank is less or equal to L. That is obviously a determinantal variety, and one can show it is not a complete intersection. And this will be my singular sets for the module that I will produce. Well, a Hilbert module is, as I mentioned, determined by its kernel function. And if it is K-invariant, it is coming from a sequence of coefficients AM, similar as the programmers. But the new point is now that they are allowed to vanish. AM are not always positive. So the case that I will look at is the module generated by a certain ideal coming from a given partition N. And in the kernel, one sees this, that only partitions show up which contain a given partition in the sense of Young diagrams. This means that the holomorphic functions in H vanish to certain orders on the strata. Now I'm running a little bit out of time, but let me try to indicate the main theorem. You all know about the Grassmann manifolds, subspaces of a given space. Now in Jordan triples, there is a generalization of this, the so-called Pierce manifolds, namely, instead of taking arbitrary subspaces of Z, you take only the so-called Pierce two spaces. I have written down an example here for a certain projection, identity 0, 0, 0, 0, 0 in the matrix space. The Pierce two space is the first corner spanned by the 1L, and there are also other Pierce spaces. So in the write-up, we will have more details. So let us leave it like that. Now, looking at these Pierce two spaces, one can define a generalized manifold, Pierce manifold, which is a generalization of the classical Grassmann manifold, which is the collection of all Pierce two spaces of a fixed rank. Even more generally, one could consider increasing flags of Pierce two spaces of a given rank, would be the Pierce flag variety. And just as in the classical case, these manifolds are compact Hermitian Kähler manifolds. Compact Hermitian Kähler manifolds, so they are quotients by parabolic subgroups, as in the classical case, as in the Borel-Walbot theorem. And in particular, they have finite dimensional spaces of holomorphic sections for any line bundle. So I'll end my talk with giving you one of the main theorems, because I cannot do much more at this time. Namely, there exists a line bundle L over the Pierce manifold M, such that the fiber at the origin, that is usually the largest fiber of my eigenbundle, is the full space of holomorphic sections of M for that line bundle. This line bundle is defined by co-cycles coming from determinants. Now, that is at the origin, that is the largest one. If W has higher rank than instead of 0, we have a similar realization, holomorphic functions, and the submanifold MW of the Pierce manifold consists of all Pierce flags such that W lies in the smallest of U1. This is, of course, the usual idea of incidence geometry. So it is an incidence manifold that gives you the arbitrary fiber. In particular, if W has maximal rank, then M sum W becomes a singleton. Of course, there is no Pierce space bigger than full rank, and VW becomes one-dimensional and is spanned by the K sub W. One final remark. Beyond this pointwise description of the eigenbundle, one can do a little better, namely on each stratum of my domain, so where the rank is equal to L, we can realize the full eigenbundle as a holomorphic homogeneous vector bundle. Not line bundle anymore, vector bundle, of course. Namely, Kc is transitive on the stratum, and the fiber is, as I mentioned in the previous theorem, the holomorphic sections of a certain Kähler manifold. QW is the complex parabolic. So this means that the whole eigenbundle is obtained by gluing holomorphic vector bundles of different rank along the different strata. So this leads to the concept of stratified Hilbert module, which is currently under active investigation. So I would like to thank you for your attention.
Thank you so much, Professor Meyer, for such an illuminating talk. I understand that there are many of us in the audience who may have lots of questions to ask, but for some reasons, there is no provision for asking questions in a preliminary talk. So, those of us who may have questions to ask are requested to write directly to Professor Meyer and seek clarifications. Well, on behalf of the IMS, we thank you again one more time, Professor Meyer, for this very fascinating talk. And we look forward to your lectures again in future. Thank you again.
Thank you, sir.
Thank you.
So I would like to request the chair to hand over the certificate to Professor Uppmeyer virtually. Thank you, sir.
Yeah. So, Professor Uppmeyer, it's a pleasure and privilege to digitally hand over this certificate from the Indian Mathematical Society to you on the occasion of your preliminary.
Thank you very much. It was a pleasure.
Yeah.
Thank you, sir.
So I thank you again, everybody in the audience.
With all your permission, can I end the meeting, sir?
Yes.
Yes.
Thank you.
Professor Uppmeyer?
I think he left.
You hear me?
No, I think
he is already left. Okay.
No, he left.
Okay.
Yeah.
Shall I, sir?
Yeah. Okay. So
Thank you, sir.
thank you very much, everybody. And